Alright, section 7.1. We are going to work on how to set up functions to be integrated to calculate quantities such as net change, area, and volume throughout this chapter. So first we're going to work on this example right here. We're going to have a function v of t that represents the velocity in meters per second of a particle moving along the x-axis. I want us to determine when the particle is moving to the right, left, or when it's stopped. We're also going to find the displacement for the time given and find the total distance traveled. So one of the things you're going to have to make sure you pay attention to is noticing and knowing the difference between distance and displacement. So here we have v of t equals to 6 sine 3t on the interval 0 to pi over 2. So to determine when the particle is moving to the right, left, or when it's stopped, we need to consider what's happening with v of t. When v of t is greater than 0, it's moving to the right. So we need to find when 6 sine 3t is greater than 0. So that means sine of 3t is greater than 0. And now using your trig, that means you need to solve for when sine of 3t equals to 0. Think about this on your unit circle. Sine is equal to 0 at 0 and pi. So that means sine of 3t equals to 0 when 3t equals to pi k, or t equals to pi over 3k. And on our given interval, 0 to pi over 2, we have pi over 3 in here, and we're going to make a sign chart. And it's going to be positive here and negative here. So that means it is moving to the right when v of t is positive, so we would say on the interval 0 to pi over 3. And similarly, it would be moving to the left when v of t is less than 0, so that means from pi over 3 to pi over 2, and it is going to be stopped when t equals to 0 and pi over 3. Now, in order to find the displacement, that means we're going to calculate the integral from 0 to pi over 2 of 6 sine 3t dt. This should be a really simple integral for you to do, so I'm just going to go ahead and tell you what the answer is, and that's 2. But in order for us to find the total distance traveled means whether you're moving to the right or to the left, you need to count those up. So that means we need the absolute value of our function. And since we did a sign chart up above and we know when the particle is moving to the right and to the left, I can rewrite my integral as the integral from 0 to pi over 3 of 6 sine 3t dt. But then I'm going to have to add it to the opposite of the integral from pi over 3 to pi over 2 because it's moving to the left. And again, a fairly simple integral for you to work out, and you're going to find that this is 4 plus 2, which equals to 6. So the total distance that he traveled was 2 to the right and 2 to the left. The total distance traveled was 4 to the right, and then he turned around and went 2 units back. That's why the total displacement was only 2 units from the beginning. Okay, example 2, we have a new problem. Here's the graph of the velocity of a particle, shown by this diagram. And we have a particle moving along the x-axis. The particle starts at x equals to 2 when t equals to 0. And I want to know where the particle is at t equals to 5, which is over here at the end of our graph, and to find the total distance traveled. So now to find where the particle is at t equals to 5, you need to pay attention to the fact that it starts at x equals to 2, and it's going to be moving to the right and then also to the left because the velocity starts out positive and it also goes negative. So using some geometry, you should be able to find out that this area is equal to 2, and this region down here, this little trapezoidal region, which has a base of 3 and a second base of 1 and a height of 2, this has area equals to 1/2 b1 plus b2 times its height. So this equals to 4 for this region down here. So if the particle is traveling 2 units to the right and then 2 units to the left again, the particle is going to be at x equals to 0 at the end of 5 seconds. However, the total distance traveled, which would actually represent the absolute value of the velocity from 0 to 5, that's simply going to be 2 plus 4, which is 6 units. And we don't take into account that it started at x equals to 2 because this is simply how far he's traveled, 2 to the right and 4 back over to the left, so he's traveled 6 units total. Alright, third example. Here I have a velocity function, v of t equals to t squared minus 8 over t plus 1 quantity squared from t equals to 0 to 5, and s of 0 equals to 9. So I want to know what the position of a particle is at 1 second, at 5 seconds, and what is the total distance traveled. So this piece right here, s of 0 equals to 9, tells you that its initial position is 9 at time t equals to 0. So if we need to find out where our particle is at 5 seconds, then we have to start out with its initial position, which is 9. So 9 plus the integral from 0 to 1 of v of t dt, that's going to give us 9 plus, and now we need to integrate our function, and that's going to be 1/3 t cubed plus 8 over t plus 1 from 0 to 1. Again, I know you guys can plug all these numbers in, so I'm going to go ahead and just tell you that equals to 16 over 3. Now when you're asked to find where the particle is at after 5 seconds, you do it the same way. We do not need absolute values in here because we're simply concerned with the position of the particle at the end of the 5 seconds. So you're going to do it the exact same way as you did the previous one. However, you're just going to change your bounds to go from 0 to 5. And once again, this shouldn't be too hard for you to calculate. You're going to get 44. Lastly, to find the total distance traveled, we need to find out the absolute value of your velocity function. And we're just going to use our calculator for this and calculate it numerically, and you're going to see it's about 42.59. Okay, the next thing we're going to do is a little bit of work. So work is the amount of force that it takes to move an object a distance d. And when you have a variable force, we say that work equals to the integral of f of x from a to b, so moving it from point A to point B. The units of work are foot-pound or Newton meters, which a Newton meter is a joule. So this is English and metric system, so just familiarize yourself with both. And we also have something called Hooke's law for springs, which is very similar to work, but it's simply work done for springs. So here we have Hooke's law saying that the force it takes to stretch or compress a spring x units from its natural uncompressed length is F equals to kx, where k is what we call the spring constant, and work equals to the integral from a to b of f of x dx. Now springs look like this, and they have a natural uncompressed state, which is if you were to take the spring and simply set it down, it's the position that it would be in, how much it's coiled up. And if you were to take the spring and stretch it, it's kind of easy to stretch it a little bit, but as you get further along, it gets harder to do, and same with compressing. So our last example, a spring requires a force of 5 newtons to stretch it 2 meters beyond its natural length. How much work is done in stretching it 5 meters beyond its natural length? So let's take a look with what we have right now. We need to find k, the spring constant. So since I know the force is 5, and we're stretching it 2 meters beyond its natural length, that means x is going to be 2. So k equals to 5 over 2. Notice I don't even care how long or the length of the spring initially. All I need to know is that it's going 2 meters beyond that natural length. So since my k equals to 2, I can write my force equation as F equals to 5/2 k, and then I can calculate the amount of work it's going to take to stretch it 5 meters beyond its natural length. So that means I have W equals to the integral from 0 to 5 of 5/2 x dx. So from 0 to 5, because 0 is the distance from its natural length to 5 meters beyond it. So again, this is a fairly simple integral. So this is 5/4 x squared from 0 to 5, and you're going to get 125 over 4 Newton meters.